Chapter 1. Opening the largest sound on Earth visual. Completely black screen. Nothing. Then, from very far away, rising as if from underground, a low-frequency, deep, organic hum. The source is ambiguous, a whale, an earthquake, something else entirely. The sound exists alone for roughly 10 seconds. What you are hearing right now vibrates at a frequency so low the human ear can barely detect it. Only a few oscillations per second, dozens of times lower than ordinary speech, far beyond the deepest notes any orchestra could ever produce. This is the sound of Antarctica's Ross Ice Shelf, and it has never stopped, not for hundreds of thousands of years. Visual, a slow fade to white, a vast, flat, frozen surface. The horizon line barely exists. The distinction between sky and ice is impossible to read. Viewed from helicopter altitude, this infinite whiteness drifts past. The light is even almost dead, Antarctica's characteristic diffuse luminosity. The Ross Ice Shelf. For more than 150 years, this place has both fascinated and terrified scientists. When the French explorer Jules Dumont d'Urville first glimpsed its coastline in 1840, he described it as an impassable barrier, and that description, perhaps, is one of the most understated in the history of science. Larger than the entire country of France, average thickness between 200 and 400 meters, in some places approaching 800 meters, and all of it in motion. Roughly 2 meters per day, nearly 3 centimeters every second. Right now, as you watch this video, the Ross Ice Shelf is drifting silently across dark ocean, toward an inevitable fate. Visual, the camera descends slowly toward the ice surface. Snow-covered, laced with cracks and folds, this surface is both beautiful and unsettling. The sound grows, now almost felt rather than heard. A vibration that resonates in the chest rather than the ear. Color palette, ice blue, cloud white, gray navy shadows. But our story today is not on the surface. The surface is only a doorway. Today we descend through that doorway, into the heart of the ice, into that dark, frozen world where seismic signals, tectonic energy waves, and mysterious rhythms science has not yet fully named are alive and moving. And down there, in that darkness, we find something breathing. This recording was made so you could hear what that something sounds like. Chapter 2. Context: what is an ice shelf and why does IT matter? Visual, infographic animation. The Ross Ice Shelf's position relative to the Antarctic continent, its dimensions, glacial flow, directions visualized. The sound continues beneath a low, soft hum. Clean but atmospheric graphic design. Let's take a few steps back first, because understanding the Ross Ice Shelf is a prerequisite for understanding what lives beneath it. An ice shelf is essentially a massive floating slab of ice that extends from a continental glacier out over the ocean. Think of it as the ocean-reaching arms of a glacier, still attached to the continent, but with water, not rock. Underneath the Ross Ice Shelf is the largest of these formations. It extends from the junction of the east and west Antarctic ice sheets out into the Ross Sea, and this region carries extraordinary importance for climate scientists. If the West Antarctic ice sheet were to collapse, a possibility discussed with growing scientific concern, global sea levels could rise by 5 to 6 meters from this region alone, from West Antarctica alone. But today we are not here to talk about glaciers melting. That is another video. Today we are talking about something much older, much deeper. Visual, the camera shifts to an animation showing a cross-section of the ice. Surface layer, middle layer, basal layer, and at the very bottom, the boundary where ice meets ocean water. An animation showing how seismic waves propagate through ice. The wave front advances from the surface inward, because this ice is alive. Mechanically, it moves constantly, compresses, stretches, bends, and those movements generate seismic waves, similar to the waves produced by earthquakes in the Earth's crust, but different, far lower in frequency, far more complex in pattern, and far more rhythmic. This is where the story begins to get interesting. Chapter 3. Seismic Signals, the Grammar of Ice Visual, the interior of a research station. Seismograph equipment, computer screens, waveform readout. A scientist examines a screen. On the graphs, regular repeating waves are visible. The environment is cold and technical, but a lit screen lends warmth. Seismology, the science of seismic waves, is usually associated with earthquakes, fault lines in the Earth's crust, magma movements, tectonic plate boundaries, but over the last 2 decades, a completely different category of signal began to catch seismologists' attention: ice-generated seismic signals, in scientific terminology, cryoseismic events. The word cryoseismic comes from the Greek cryo, cold ice, seismos, vibration, tremor, vibrations born of cold dot, and the Ross Ice Shelf is the richest source of these vibrations on the planet. Visual waveform graphs shown in close-up as the narrator continues. Regular rhythms and periodic repetitions are highlighted on the graphs. An animation marks specific repeat points in the wave pattern, like beat markers in a musical score. In 2018, researchers at the University of Chicago made an extraordinary discovery using a network of seismometers placed across the Ross Ice Shelf. The ice was vibrating continuously, every hour of every day, every season, without pause. But the more remarkable thing was this: these vibrations were not random. They were rhythmic. They produced a measurable pattern that repeated at regular intervals, like a heartbeat that could be timed. The researchers first suspected instrument failure, then data processing errors, then other explanations, but in the end they were forced to accept the ice really did vibrate this way, and the reason was something both far simpler and far more extraordinary than they expected. Wind. Visual. A fierce wind moves across the ice surface. Snow particles rake the surface like blades. This image is shown in slow motion, while an animation shows how sound passes through that surface and propagates into the ice below. The wavefront moves from the surface inward. Antarctica's winds are the most violent on Earth, known as katabatic winds. These airflows descend from the continent's high interior down toward the coast, reaching extraordinary speeds, above 300 kilometers per hour, beyond even Category 5 hurricanes, that as these winds sweep across the surface of the Ross Ice Shelf, they drive a thin layer of snow in constant motion. That motion creates friction against the ice surface. Friction generates vibration. Vibration becomes seismic waves. But the truly extraordinary part is this: these vibrations align precisely with the resonant frequencies of the ice itself, exactly like a musician playing a note that asterisk perfectly matches the resonant frequency of their instrument. The ice amplifies these vibrations, transmits them over long distances, concentrates them at specific frequencies. The result? The Ross Ice Shelf behaves like a natural musical instrument, a vast instrument made of ice, playing without pause. Chapter 4. Infrasound. What we cannot hear visual, an infographic showing the human hearing frequency range. The band from 20 Hz to 20,000 Hz is displayed. Then the infrasound region, the 0.525 Hz band far below this range, is highlighted. A figure of a human with the zone outside hearing range shown in a cool blue tone. Let's go a little into physics now. But don't worry, this section is more about philosophy than physics. The human ear can detect sound waves oscillating between 20 and 20,000 times per second. That range is called the auditory frequency range. Sounds below 20 Hz are called infrasound, subsonic or low-frequency sound. The vibrations of the Ross Ice Shelf inhabit largely this low-frequency zone, ranging from a few oscillations per second to a few dozen, so you cannot hear them directly, but you can feel them, visual, someone's hands on a vibrating surface. They are feeling the vibration through their palms. Their expression carries both curiosity and a faint unease. Slow motion. The surface beneath their hands might be ice, or simply vibrating wood. What matters is the acoustic concreteness of the sensation. Infrasound can produce strange effects in the human body. Internal organs, eyeballs, the vestibular system, all of these have their own resonant frequencies, and those frequencies fall close to the infrasound range. In theory, a sufficiently powerful infrasound source can trigger dizziness, visual distortions, a sense of panic, and according to some reports, even hallucinations. Some researchers have proposed that a portion of ghost stories and reports of eerie places are actually in old factories, basements, historic buildings. Some of these were claimed to contain natural infrasound sources, and those sources were allegedly generating an inexplicable sense of dread in people who spent time in them. This is not purely speculative. Some experimental studies have shown that certain infrasound frequencies increase subjects' self-reported anxiety in mild visual anomalies, but the methodology is contested. Science has not yet reached a definitive verdict. What is not contested is this. The infrasound signals produced by the Ross Ice Shelf have been directly recorded by researchers, and when those signals are processed and shifted into an audible frequency range, as if accelerated thousands of times over, the resulting sound has been described by many listeners as disturbingly organic, and that is exactly what we mean to show you. Chapter 5. Transformation from seismic data to melody visual, a computer screen. Audio editing software open. Raw seismic data waveforms, transformation steps animated. Left panel, raw seismic wave. Right panel, processed audio waveform. The mathematical bridge between the two is visualized. Before telling you the story of how this recording was made, I need to explain the method. Because converting seismic data to sound sounds mystical, but it is actually a very concrete operation. Seismic data is, at its core, a record of vibration. Seismometers are instruments that convert ground movement into a digital signal. The waveform that signal produces looks visually like a sound wave. Strong vibration at peaks, weak vibration in troughs. Dense waves indicate high frequency. Sparse waves, low frequency. The basic method for auditory sonification of seismic data is this. When the recorded vibration data is loaded into audio playback software, the frequency of the resulting signal is elevated, a process called pitch shifting or time compression. For instance, a signal oscillating 3 times per second, when shifted to 300 oscillations per second, becomes a sound within the human hearing range, but something critical happens in this process. The patterns within the signal are preserved. If the original seismic data contained rhythmic repetition, the converted sound will also be rhythmic. If certain frequency concentrations existed in the original, those frequencies will come forward in the processed version 2. And when the Ross Ice Shelf's seismic data was subjected to this transformation, the resulting sound shocked many of its listeners. Visual, the screen darkens. Only the visual representation of the sound, a waveform animation, is visible. The waveform pulses, rhythmic patterns form. Color palette, ice blue waveform on a dark background, and the sound begins. Note, the processed sound recording plays at this point approximately 2 to 3 minutes. Duration and the specific passage selected should be coordinated with the video's sound designer. Visual, while the sound plays. Footage from beneath the ice shot with dive cameras. Looking up from beneath the ice toward the sea floor drifts slowly past. Turquoise and blue light refractions. Ice stalactites. Profound silence. A waveform visualization runs as a thin strip over the imagery. What you are hearing is the vibration of the Ross ice shelf, not in its raw form. It has been shifted into a frequency the human ear can detect, but the patterns within it have been taken directly from the original seismic data, unchanged. Nobody composed this melody. Nobody programmed this rhythm. This sound comes from the ice itself. Chapter 6. The History of the Research. Those who heard the Ice Visual Archive photographs. Robert Falcon Scott, Ernest Shackleton, Roald Amundsen, black and white images, antique-looking maps, portraits of explorers, sepia tone filter, period music barely audible behind. The first people to see the Ross ice shelf also heard its sounds, but they had no way to make sense of what they were hearing. 1841, the ships Erebus and Terror under the command of James Clark Ross were pressing southward. Ross wanted to reach the magnetic South Pole, but his path was blocked by a colossal wall of ice. This barrier, in places rising 150 meters above the sea like a sheer cliff face, was unlike anything he had encountered. Ross was an Arctic explorer. Ice was not foreign to him. But he had never seen a body of ice this vast, this magnificent, and this body of ice was making sounds, creaks, groans, occasional deep booming rumbles. Ross's journal contains entries referencing these sounds, but at the time they were attributed to the mechanical motion of glaciers' compression, friction, stress, a completely accurate observation but only a small piece of the story. When you read the archive carefully, you encounter in Ross's account not just the excitement of discovery, but a strange mixture of awe and helplessness. No power at man's disposal could breach such a barrier, he writes at one point. It is as if the continent says, no further. The continent was saying exactly that, but in its own language, with vibrations, with seismic waves, and Ross had not yet learned that language. No one had visual archive footage from the early 1900s. Photographs from Amundsen's or Scott's expeditions, people working in punishing conditions, frozen equipment, figures standing at the edge of ice crevasses. The images convey both courage and vulnerability simultaneously. A century later, when Robert Falcon Scott and Roald Amundsen entered their race to the South Pole, the Ross ice shelf became a base of operations. Both teams established field camps on the shelf and were forced to manage their explorations from this frozen platform. Members stationed at Amundsen's winter quarters at Framheim reported that the ice produced strange sounds at night. Some found it unsettling. Several wrote that the ice seemed to be speaking in journals from the period. These accounts are delivered typically in parentheses and with apologetic qualification. This may sound absurd, but perhaps it was only exhaustion. I may, of course, be mistaken. They were not mistaken. Similar testimony exists in Scott's final expedition too. Careful biographical research reveals informal discussions among crew members about the sound of the ice at night. Some rationalized it as wind and cracking. Others listened in silence. One man wrote this: I had never thought the world could be this loud. Standing on an ice shelf, in temperatures that could kill within minutes, this man had heard the sound of the ice, and it had surprised him. Visual, transition to modern research equipment, seismic sensors, data collection stations, satellite-linked modern research units. The images are both technical and solitary. This equipment works without human presence, alone on the ice. When modern seismology arrived in Antarctica in the second half of the 20th century, our understanding of ice dynamics changed fundamentally. Seismometers began capturing signal patterns never recorded before. Initially, these signals were attributed to tectonic activity. The Antarctic continent is in fact a geologically active region. There's volcanic activity, there is tectonic plate movement, but certain signals could not be explained by tectonic activity. Their frequencies were wrong, their locations were wrong, their periods were wrong. These signals were coming from the ice. Chapter 7. The Chicago Study. What Science Heard in the Ice Visual. Modern research paper visuals, scientific graphs and tables, an academic environment but in the visual language of the video, framed not as a dull presentation but as a dramatic story of discovery. The 2018 paper represents one of the most comprehensive studies on this subject. Julian Chaput and his team's broadband seismometer network, deployed across the Ross Ice Shelf, collected uninterrupted data, and when that data was analyzed, the results were striking. The ice was generating a continuous seismic noise. The source of this noise was wind-driven vibrations on the surface snow, and these vibrations were interacting with the acoustic properties inside the ice, concentrating certain frequencies, generating specific patterns. The study's most remarkable finding was this. These vibration frequencies changed in response to wind speed and surface conditions, as if the ice shelf were reacting to changes in its environment. When the wind intensified, frequency rose. When surface temperatures shifted, the pattern changed. The researchers offered a metaphor. The ice shelf behaves like nature's continuously playing musical instrument, and the timbre of this instrument, the character of the sound it produces, changes constantly with environmental conditions. Visual graphs showing oscillations, a period of high frequency, intense vibrations, then a period of lower, slower vibrations. Below these graphs, wind speed data for the same time intervals. The correlation is visually unmistakable. The animation is slow and deliberate. The viewer sees the relationship with their own eyes. This study has an enormously important practical application by monitoring seismic vibrations. The health status of the ice shelf can be tracked. Stresses and cracks within the ice alter the vibration pattern. These changes can serve as early indicators of a potential calving or collapse event. So the ice shelf is, in a full and literal sense, talking. And for anyone who is listening, this conversation contains information that can be extracted. Science is pushing against its own boundaries, but some questions remain unanswered. When I first read this study, I thought, for centuries people had been hearing this sound, Amundsen's team, Scott's team, Ross's sailors, but they had not yet learned the language needed to understand it. Perhaps the greatest discoveries don't arrive with the sound itself, but only after we find a language capable of reading it. Chapter 8. Deeper questions. Why does rhythm exist? Visual, dark, deep underwater footage. The view from beneath the ice. Light filters down from above. Deep water. Silence and slow movement dominate. In this section, images are selected less to inform and more to meditate. Now we come to the most compelling part of the story. The Chicago study proved the ice vibrates, but why do these vibrations exhibit a regular rhythm? Wind is chaos. It is turbulence. The atmosphere is an extraordinarily complex nonlinear system. Wind speed changes every minute. Direction constantly deviates. The distribution of snow across the ice surface is not homogeneous. Nothing, in any true sense, is regular. And yet when you look at the seismic data, you see periodic repetitions, as if there is a metronome, as if something is keeping time busy. Visual, rhythmic oscillations on graphs, close-up, mathematically equal intervals are highlighted, almost musical notation symbols are briefly overlaid on the graph, then removed, a metaphor, only visual. The sound design should be careful here. Several explanations can be offered. First, resonance. The ice shelf has specific natural frequencies. Vibrating at those frequencies is easier than vibrating at others, exactly. Like a musical instrument vibrating far more powerfully at its resonant frequencies, so even a chaotic stimulus passing through the system can emerge as something regular. Second, the ocean. There is ocean beneath the ice shelf, and ocean waves are lifting and lowering the ice shelf at specific, well-defined frequencies on a regular schedule. This ocean loading effect creates its own vibration pattern within the ice. Third, tectonics. The Antarctic continent is geologically active. Seismic waves from distant earthquakes, as they pass through the continent, also excite vibration in the ice shelf, and these vibrations to concentrate at certain frequencies. Fourth, and this is the most extraordinary thermodynamics within the ice that are not yet fully understood. Ice behaves like an enormous heat reservoir. It absorbs solar energy at the surface, transfers it slowly inward, and releases it again over long cycles. These thermal cycles produce mechanical changes. Mechanical changes generate vibrations, and those vibrations can synchronize with the rhythm of the thermal cycle, so perhaps the ice's rhythm is the rhythm of the sun, the rhythm of the ocean, the rhythm of the earth itself. And if so, if this melody is the song of the earth itself, then when we hear it, we are hearing something far larger than a geological formation. Chapter 9. Fractals and scale, vast order in the smallest ice visual, fractal mathematical animations. The Mandelbrot set, Julia sets. Fractal examples from nature, snowflakes, branching trees, river deltas, coastlines, and then crack patterns within ice, following the same fractal logic. Transitions between visuals are smooth, mathematical aesthetics are foregrounded. Fractal. What did you think when you first heard that word? Abstract mathematics, perhaps? Complex computer visuals, perhaps nothing at all? Fractal means, in brief, a geometric structure that repeats the same pattern regardless of scale. Every leaf of a snowflake mirrors the shape of the entire flower. Every branch of a tree carries the shape of the whole tree. Every kilometer of a coastline exhibits the same complexity as the full 100 kilometers. Ice forms one of nature's finest fractal examples. At the micrometer scale, ice crystals too small to see. At the millimeter scale, snowflakes. At the centimeter scale, surface texture and roughness. At the meter scale, ice stalactites and protrusions. At the kilometer scale, crevasses and folds. At the hundreds of kilometers scale, the ice shelf itself. At every scale, the same underlying pattern. At every scale, the same mathematical logic. And this fractal structure is reflected in the vibrational behavior of ice as well. Small-scale vibrations are mathematically related to large-scale vibrations. The oscillation of a single ice crystal resembles the oscillation of a crack 100 kilometers long. This explains why the sound of ice feels so organic, so alive, because organisms, living things, also exhibit fractal patterns in their biological processes. The branching of the lungs is fractal. The vascular system is fractal. The folds of the brain are fractal. Even the heartbeat, in mathematical analysis, shows fractal properties. The boundary between living and non-living through fractal mathematics blurs, and that blurring, is it disturbing or is it wonderful? Your answer is probably both. Chapter 10. Beneath the ice, physical reality, visual preparations for a dive operation. Researchers at a site in Antarctica descend through an ice borehole, Real archival footage. McMurdo Station ice dives are a comparable research operation. The technical scale of the operation is visible, but the human dimension is foregrounded. Subice diving is among the most demanding and, simultaneously, most mesmerizing research operations in the history of science, and research dives beneath the Ross Ice Shelf. Scientists can descend to depths of approximately 400 to 800 meters, equivalent to 2 to 4 times the height of the Empire State Building, and along that entire distance there is a frozen ice ceiling above. The only exit back to the surface is the hole you descended through. Researchers who work in this environment describe a strange acoustic world. They hear things they do not hear at the surface. They feel the ice groaning, cracking sounds, creaks. These are expected. But there is also a constant, low-frequency sense of presence. Some describe it as, "I had the feeling the ice was breathing." Visual underwater camera footage, looking upward toward the ice ceiling. Turquoise and blue color tones, light refractions. Ice stalactites, a composition that creates a deep sense of silence and solitude. Stalactites hang down from the ice ceiling, ice shaped by contact with water. The image is both beautiful and unsettling. Some of that feeling is psychological. Being beneath the ice, in an environment with a single exit, under hundreds of meters of frozen ceiling, triggers fundamental survival instincts in the human brain. People who have never developed claustrophobia report working very close to a mild panic threshold in this environment. But some of it is not psychological. The vibrations are genuinely there. The sounds are genuinely there. The ice genuinely resonates at certain frequencies, and the human body can partially sense those vibrations not through the ears but through bones, through muscles, through organs. That must be an extraordinary experience. Extraordinary in both a scientific and an existential sense. A researcher who had been stationed at McMurdo told me this. The strangest feeling when working under the ice was this. You felt as though the ice was watching you. Of course it wasn't, but the vibrations came from every direction. You lost your sense of orientation, and in that moment you understood that you were actually inside the ice, standing in a void within the ice. Inside it, Chapter 11, Time a Duration That Cannot Be Divided, visual imagery conveying the passage of time. Sunset and sunrise in Antarctica, the sun does not set but traces an orbital circle. Transformation is slow but constant. The same mass of ice in different light conditions, 2 a.m. and 2 p.m., same ice, different light, but the ice has not changed. Estimating the age of the ice in the Ross Ice Shelf is a question that sits at the intersection of geology and biology. Ice core, the research method in which long cylindrical samples are drilled from within the ice, offer extraordinary information about the past. Ice accumulates in layers. Each year's snowfall settles on top of the previous year's, compresses over time, and transforms into glacial ice. These layers, exactly like tree rings, carry time within them. Some of the Ross Ice Shelf's ice is thousands of years old. Certain sections are tens of thousands of years old, and the air bubbles trapped in this ice preserve a fraction of those eras' atmospheres. Through ice core analysis, we can detect the atmospheric composition, temperatures, and even volcanic eruptions of tens of thousands of years ago. This ice is a time machine. Visual ice core samples in a laboratory. Thin, translucent cross-sections photographed under light. Air bubbles are visible inside. Perhaps a scientist's hand holds the core like holding the past. This visual metaphor will strengthen this section of the video, and the vibrations of this time machine are, perhaps, the audio record of this accumulation over thousands of years. The stress, the compression, the slow flow frozen into the ice across millennia, all of it is stored as mechanical energy and periodically released as vibration. Waves. The sound you are hearing right now may be an instantaneous expression of energy accumulated over thousands of years. That this idea stayed with me. While listening to the recording, at one point I thought, this is not the sound of the ice. This is the sound of time. And if that is true, if the ice is in some sense converting time into vibrations, and when those vibrations become audible, the past is touching us, then listening to this recording is not just an interesting scientific experiment. It is hearing the voice of history. Chapter 12. Other ices, similar formations around the world, visual, a world map. From Antarctica to the Arctic, then Alaska, Greenland, Iceland. Similar ice formations are highlighted in each region. The map is simple and clean. This is a journey, not a lecture. The Ross Ice Shelf is not alone. Similar cryoseismic signals are being recorded across the planet. The Greenland ice sheet, particularly during summer, is an intensively studied field for investigating the relationship between surface meltwater and subglacial seismic activity. Findings here show that ice loss is occurring far more rapidly than previously understood, but at the same time, the seismic sounds within the ice reveal the complexity of the processes. A glacier doesn't simply melt, it transforms, slides, bends, fractures, and each of those processes leaves its own acoustic signature. Glaciers in Alaska and Canada are being studied for the seismic signals generated by what is called basal sliding. A layer of water beneath a glacier facilitates the glacier's movement across the bedrock. This sliding process, like dragging a 100 million structure across a surface, leaves a seismic imprint. Iceland is a unique laboratory where volcanic and glacial activity are completely interwoven. Their volcanoes sometimes erupt beneath the ice. Magma movements beneath the ice sheet generate vibrations, and those vibrations alter the glacier's movement model. Two chaotic systems, volcanic and glacial, talking to each other through seismic waves. Visual footage from Iceland of lava breaking through ice, red light and blue ice, a dramatic, almost sacred contrast. Fire and ice. This is one of the most powerful visual contrasts available. And the Arctic, the sea ice around the North Pole is shrinking, but even within that shrinkage process, vibration patterns are being monitored. The fracturing, breaking, and calving of the ice cover all leave seismic imprints, and these imprints provide new tools for tracking the rate of climate change. Ice speaks the same language in every corner of the world. The language of vibration, and that language has been spoken for millions of years. We have only just, in the last few decades, begun to learn to read it. Perhaps this learning came just in time. Chapter 13. Whales and ICE connections with other listening beings. Visual. Blue whales in Antarctic waters. Humpback whales, giant marine mammals swimming at ice edges. Beneath them, fully blue and deep, above them, ice and white. The image is majestic and quiet. Music and effects in this scene should be minimal. We recorded these sounds, processed them, and listened to them, but these sounds are already being listened to by others, and perhaps for much longer than we have. Whales use a very broad range of the sound spectrum. Humpback whale songs range from 10 to 4,000 hertz. Blue whales communicate at far lower frequencies below 10 hertz, dropping as low as 1 hertz in some cases. These frequencies travel hundreds to thousands of kilometers through water. And the infrasound signals produced by the Ross Ice Shelf overlap with this frequency range. Theoretically, a blue whale hundreds of kilometers away may be hearing the vibrations of the ice shelf. Visual, underwater sound visualizations recorded with hydrophones. Whale songs and ice vibrations shown on the same spectrogram. Their visual overlap creates a dramatic effect. Two separate color codes, whale sound in amber, ice sound in blue. These two colors meet in a shared region. This is not purely speculative. Hydroacoustic research conducted in the Antarctic region showed that whale sounds and ice-generated sounds are concentrated in the same frequency band. How whales adapt their communication strategies within this crowded frequency environment has become a question of growing interest too. Researchers in recent years, some researchers have proposed that blue whales use ice shelf signals as flares. The ice's vibrations may serve as a reference point for certain route information or position estimation. Not proven, but not speculative enough to be dismissed. If this is true, if whales are genuinely hearing the ice shelf's sound and using it in a meaningful way, then the ice shelf is not merely a physical formation. It is an active sound source within the ecosystem, part of a network of signals on which living creatures depend. The ice is speaking, and perhaps the whales are answering. And this is not simply a romantic metaphor. If the ice shelf vanishes, these signals vanish too, and creatures that rely on them, if they exist, lose a navigational aid or a communication channel. This is an ecological loss, an acoustic loss, in some sense, perhaps, a loss of language. Chapter 14, Climate Change and the Changing Voice of Ice Visual, Time Series Imagery from Antarctica, the changing size of the ice shelf over time, increasing cracks, calving events, dramatic but not speculative presentation, data-based visualization. The Ross ice shelf is changing. This is not an opinion. It is a measured fact. Over recent decades, the mass, extent, and internal structure of the ice shelf have undergone significant change. Surface melt has increased. The ocean water beneath it has warmed. The base of the ice has slowly but measurably retreated. And when you look at the seismic records, the acoustic signature of these changes is visible too. Visual comparison of seismic data from different eras. Early 2000s alongside early 2020s. Differences in frequency patterns, intensities, and rhythmic characteristics are visualized. Two graphs side by side, past on the left, present on the right. Differences are highlighted by animation. When researchers compared seismic data series collected over the years, they found this. The ice's vibration frequencies are shifting. As the ice surface mass decreases, the resonant frequency changes, exactly like a musical instrument's string producing a deeper sound when loosened as the ice shelf changes. It begins to produce different sounds. This finding carries enormous practical significance. Theoretically, the ice shelf's real-time health status can be monitored from seismic data alone. Without satellite imagery, without deploying teams on the ground, by analyzing sounds from within the ice, it may be possible to forecast where and when the shelf is weakening. The ice speaks before it dies, and for those who can hear it, the future may be readable, but this need not be a story of grief, because the ice shelf is still here, still vibrating, still speaking. In 2002, the Larsenby ice shelf collapsed. This collapse was recorded by seismometers placed in the region. In the seismic data, a clear change was visible before the collapse. Vibration patterns gave signals, indicating that structural integrity had begun to fail. But at that time, no one had a system in place for real-time interpretation. This time we are listening. The Ross ice shelf is being monitored continuously, automatically, with high-precision systems. In this time, if the sounds change, we will notice. Chapter 15, Sound Art and Nature, Other Transformations Visual, Various Natural Sound Transformation Projects, NASA's Conversion of Space Data to Sound, Ocean Floor Seismic Recordings, Vibrations of the Solar Corona, visual presentations of these projects. The conversion of scientific data to sound has become a rapidly growing field over the last 20 years. Known as sonification, this process is used both for scientific analysis and for artistic applications. NASA converted the vibrations of the sun to sound. The sun's surface is an ocean of plasma in continuous vibration. These vibrations were captured by radio telescopes and shifted into the audible range. The resulting sound strikes many listeners as deeply organic, almost like a musical instrument. Black holes have been given sound in a similar way. The vibrations of the black hole at the center of the Perseus galaxy cluster were shifted, approximately 57 octaves upward from the original. The resulting sound is, to some listeners, deeply unsettling, like a hum arriving from the void. The sound of a black hole. Did you ever think about that? Visual, humpback whale songs and ice shelf signals visualized simultaneously. 4. Seismic activity. Submarine volcanic movements, a collage of nature's diverse voices. Ocean floor researchers monitored volcanic activity along mid-ocean ridges using both seismic and acoustic methods. In these regions, layers of water, temperature, and salinity alter the way sound propagates. Some frequencies travel thousands of kilometers, effectively forming a sound channel inside the ocean, and this channel provides a natural infrastructure for both human and marine mammal communication. The Earth is speaking. It always has been. The ear simply had not been trained sufficiently. The Ross Ice Shelf produces one of the most powerful and most mysterious voices in this conversation, and this sound has caught the attention of other sound artists as well. Some composers have integrated seismic data into musical compositions. Some installation artists have built systems that convert ice shelf data into real-time sound performances. This bridge between science and art has grown steadily stronger over the last decade. Chapter 16. The ghostly rhythm. Why does this sound disturb us? Visual, a quiet, dark corridor, an empty hallway in an old building. Then, giving the same feeling but entirely different in image, the boundless, empty ice shelf. The sense of solitude is identical in both images presented in parallel montage. I need to say something about why this sound is found so disturbing, because this sound has been described by many listeners as ghostly, unsettling, organic but inexplicable, as if coming from a living thing, but belonging to nothing living. This perception has entirely psychological foundations, and it points to a remarkably interesting psychological phenomenon. The human brain evolved to recognize certain patterns, rhythm, repetition, regular intervals. These are the signs of life. A heartbeat is rhythmic. Breathing is regular. Walking is rhythmic. Even speech is rhythmic. So when the human brain hears a rhythmic signal, it automatically asks, is this coming from something alive? Who is there? Visual, brain activity, imagery, fMRI scans. Brain regions associated with agency detection are highlighted. Then, a transition to ice shelf footage, a gaze, searching for an agent in that boundless whiteness. This reflex is known as hyperactive agency detection. At every stimulus that might indicate danger or significance, the brain searches for an agent, an active entity. Evolutionarily, this makes sense. The cost of a false positive perceiving a non-existent threat is low. The cost of a false negative missing a real threat can be fatal. When you listen to the processed sound of the Ross Ice Shelf, your brain hears a rhythmic pattern, and it immediately asks, who is there? There being no reasonable answer available, the ice is not alive, but it seems to behave as if it is. The brain is left in a state of strange ambiguity, and this ambiguity produces a mild discomfort, a mild fear, a mild I cannot understand this sensation. I gave this sensation a name. the ghost of the ice. This ghost is not real, but the sensation it produces is and perhaps this ghost is teaching us something important. The boundary between living and non-living is, from an evolutionary standpoint, one of the most critical boundaries of all. The brain is extremely sensitive to recognizing this boundary, perhaps hypersensitive, and the ice shelf challenges this boundary with its rhythm, its pattern, its quietly insistent impression of life. Chapter 17. The recording process, how this video is made visual. In the background, audio editing software waveforms, seismic data graphs. A researcher or sound artist processes this data. Screen captures should look real, not fake or representative. The sound you hear in this video was obtained from actual raw ice shelf seismic data. Raw seismic recordings were drawn from publicly accessible research databases. These data were recorded by broadband seismometers placed by seismic network stations. The processing steps were as follows. Step 1. Cleaning the raw seismic data. Seismic recordings contain signals from multiple sources. Tectonic noise, equipment vibration, phase waves from distant earthquakes. A frequency filter was applied to distinguish between these. Target frequency band, 0.525 Hz. The band in which ice-generated vibrations concentrate. Step 2. Pitch shifting frequency transposition. The selected data was shifted into the audible frequency range. Throughout this process, the original structure of the signal was preserved, only its frequency was elevated. Approximately 100 times speed increase was applied. This means moving from the original signal's 1 or 2 oscillations per second to 100 to 200 oscillations per second. Step 3. Dynamic range normalization. The processed sound has a very wide dynamic range. There are very quiet sections and very loud sections. Normalization was applied so listeners can hear both the calm and the intense passages. Step 4. Minimal musical a very faint drone tone, in the same frequency range, was added beneath the seismic sound. The purpose of this tone is to sustain the listener's attention and to bridge the silent moments when the seismic signal would otherwise disappear. But note, this is support, not signal. The primary sound is real, visual, 2 layers visible in the waveforms, one the processed seismic data, the other the musical support. How light the second layer is becomes visually clear. 90% signal, 10% support. This ratio is represented visually. This distinction is important to emphasize, because some natural sound content is largely produced, drawing only a touch from nature. This video is not that. The musical layer exists as a support for the seismic signal, not to build something artificial on top of ice in order to make the sound beautiful. The voice of the ice shelf is already beautiful enough, already compelling enough. All it needs is to be carried into a frequency where it can be heard. Chapter 18. 48 hours. Why this duration? Visual, a short but striking time-lapse. 48 hours pass across the ice shelf. The sun traces its orbital arc. Light changes, the surface appearance shifts. A clock indicator can be included, but it should be small. The title of this video contains 48 hours, and this is not an arbitrary number I chose. Ross. Ice shelf seismic data exhibits 48-hour cycles. Not exactly, nature does not deal in exactness, but a clear, approximate 48-hour rhythm is present. It is thought that this rhythm arises partly from a semilunar interaction between the moon and the ocean tidal loading. The ocean tide runs on a 24 to 25-hour cycle, but over longer-term integration, certain seismic patterns trace a 48 to 50-hour larger cycle. This is striking, because humans have an approximately 48-hour rhythm too. The sleep cycle is 24 hours. But some biological processes, hormone cycles, immune system activity, mood oscillations, show meaningful patterns. When examined on a 48-hour period, there is no causal connection between the ice shelf's 48-hour rhythm and the human 48-hour biological cycle. One is the product of the moon and the ocean. The other is the product of evolutionary biology, but thinking about them together provokes a strange sensation. Perhaps the universe has a tendency to produce certain rhythms, perhaps even chaos, if you wait long enough, resolves into rhythm. Or perhaps it is simply coincidence. I don't know what science says about this, but the sensation is powerful. And this video is dedicated to 148-hour span, to a full cycle of the ice shelf. Listen through it from beginning to end. Feel how the sound changes, how the rhythm breathes. This is not a scientific experiment. This is a listening meditation. Chapter 19. The Human in Antarctica Existential Scale Visual. A single human figure at the center of an infinite white ice shelf. Small, almost invisible, but they're not looking at the camera, looking at the ice surface, or at the distant horizon. When you talk to researchers who have been to Antarctica, who have worked there, they all share a common experience: scale shock. Antarctica is a place that cannot be conveyed photographically. Photographs cannot capture its scale. There are no dimensional references. In a photo frame you see mountains, ice, sky, but you cannot tell that mountain is 50 kilometers away. The reason a human figure appears in the frame is not that humans are small, it is that the environment is this vast. This vastness produces a strange psychological effect in people. Researchers describe it as existential disruption. The boundaries of the self become blurred. The line between I and beyond dissolves. You feel very small inside something very large. But this smallness is not crushing. It is, rather, a relief, as if you are being released from a burden. Visual, night sky, the aurora australis over Antarctica. Aurora australis, green and purple bands of light falling on ice, above and below, are equally bewildering and incomprehensible. There is an acoustic dimension to this sensation as well. In Antarctica, silence is different. In moments without wind, which are rare, there is a genuine silence. The ears begin to ring, because the auditory system is expecting noise and receiving nothing. And within this silence, if you pay attention, the ice makes sounds: a distant crack, a soft creak, a low, incomprehensible vibration from very far away. When scientists encounter these sounds, they generally stop first, check their recording equipment, look around, smile, and then write in their notebooks. One person told me, "In that moment, we felt like guests, not the ice." That sentence left a deep mark on me. Guests, we are guests here, and the hosts, ice, ocean, wind, time, are not even aware of us. Chapter 20. The Future Sound. What happens if the ice retreats? Visual to side-by-side images. Left, the Ross Ice Shelf today. Right? Projection models, forecasts for half a century or a century hence. The difference between the two is presented concretely. We have arrived at the science fiction section of this video. Speculative, but not empty. Speculative based on real models. Real data if the Ross Ice Shelf continues to shrink. And the current trajectory points in that direction. The ice shelf's vibration patterns will also change. Less mass, different resonance, different surface area, different wind surface interaction, changing ice-ocean boundary, different thermal dynamics. A theoretical scenario as the ice shelf diminishes. It retunes as a natural musical instrument. Frequencies rise, rhythm accelerates or slows, and at some point, when the shelf has shrunk sufficiently, the vibration patterns change entirely. Monitoring this change matters. both scientifically and emotionally. Visual, an iceberg calving from the ice shelf. Enormous, silent, slow, drifting out into the ocean, alone separated from the ice shelf, but still vibrating with its own intrinsic vibrations. Retuned to its new environment, in 2002, the Larsen B ice shelf collapsed. The collapse was recorded by seismometers deployed in the area. In the seismic data, a clear change was visible before the collapse. Vibration patterns gave signals indicating that structural integrity had begun to fail. The ice gave sound before it collapsed, but that sound was not heard by anyone at the time. Retrospective analysis noticed these warning signs. This time we are listening. The Ross Ice Shelf is being monitored continuously, automatically with high-precision systems, and this time, if the sounds change, we will notice. I hope we listen long enough before they change. I hope we can understand what the sound was saying before it falls silent. Chapter 21, SLEEP. Consciousness and ICE. Why does this sound induce sleep? Visual. Someone in deep sleep, a slow transition over ice shelf imagery. Sleep and ice are composed in visual parallel, both quiet, both endless. I have learned that this recording has been used by many listeners for sleep, and this both surprised and did not surprise me. It did not surprise me because sleep researchers have repeatedly shown that sounds with certain acoustic properties facilitate the transition to sleep. In particular, pink noise sound with a power that decreases linearly across the frequency spectrum improves sleep quality, and the vibrations of the ice shelf, in their processed form, approximately carry this pink noise property. Rhythmic sounds that repeat at regular intervals but change, also move us toward the delta and theta brainwave states associated with sleep. Just like the sound of rain or ocean waves inducing sleep, visual brainwave graphs, changing frequencies across sleep stages. Delta waves, deep sleep, are visualized. In parallel, ice vibration frequencies. What surprised me was this. This sound is also described as eerie. And normally eerie things are not expected to put people to sleep. But perhaps this is not a contradiction. Perhaps vast and incomprehensible things can give both fear and peace simultaneously, like sleeping beside the ocean. Hearing the sea is both calming and raises the question, what is out there? The sound of the ice shelf is like this. It draws you toward a center while simultaneously exceeding you. And when these two things happen at once, perhaps consciousness lets itself go, dissolves into something larger. This is the essence of sleep, releasing the self, and the Ross Ice Shelf is extending an invitation to that release, with its vibrations, its rhythm, its sound that you cannot understand but you can feel. Chapter 22, Phonography Preserving Sound. Transmitting sound visual, a historical montage from Edison's phonograph to today's digital recording technology. Summary imagery from the history of sound recording, black and white to color, analog reel to digital file. The invention of sound recording was one of humanity's greatest ontological revolutions. Before it, sounds were transient. A word was spoken and it was gone. A melody was played and it faded, a person's voice. After that person died, lived on only in the memories of others. After Edison's phonograph, it became possible to capture sounds on a physical medium. This was a revolutionary change. A dead person could now speak in their own voice. An orchestra from a century earlier could play again. Now we are taking this further. Not just human voices, we are recording the sounds of the world. The vibrations of glaciers, the murmur of the ocean floor, the pulsations of the sun, visual, digital storage, imagery, server centers, databases, digital archives. Then a reversal. ancient air bubbles trapped in ice. Both are archives, both are time capsules. Ice is itself an archive. Air bubbles millions of years old. Dust particles carried by ancient winds, volcanic ash, all stored within the ice. This archive offers unique information about the history of the planet. And now, we are recording the ice's own vibrations, the voice of the ice itself, and transmitting this recording to future generations, perhaps in 100 years. The Ross Ice Shelf will no longer exist at this scale, and perhaps the people of that future will listen to this recording and think, that is how ice sounded back then. That is how large the ice was. And will this recording be a source of longing, a warning, a document of wonder? I don't know, but we are keeping the record. For now, that is enough. And keeping records is perhaps one of humanity's most beautiful qualities. We are transient, but the sounds we leave behind may outlast us. Chapter 20. The Future Sound. What happens if the ice retreats? Visual to side-by-side images. Left, the Ross Ice Shelf today. Right? Projection models, forecasts for half a century or a century hence. The difference between the two is presented concretely. We have arrived at the science fiction section of this video. Speculative, but not empty. Speculative based on real models. Real data if the Ross Ice Shelf continues to shrink. And the current trajectory points in that direction. The ice shelf's vibration patterns will also change. Less mass, different resonance, different surface area, different wind surface interaction, changing ice-ocean boundary, different thermal dynamics. A theoretical scenario as the ice shelf diminishes. It retunes as a natural musical instrument. Frequencies rise, rhythm accelerates or slows, and at some point, when the shelf has shrunk sufficiently, the vibration patterns change entirely. Monitoring this change matters, both scientifically and emotionally. Visual, an iceberg calving from the ice shelf. Enormous, silent, slow, drifting out into the ocean, alone separated from the ice shelf, but still vibrating with its own intrinsic vibrations. Retuned to its new environment, in 2002, the Larsen B ice shelf collapsed. The collapse was recorded by seismometers deployed in the area. In the seismic data, a clear change was visible before the collapse. Vibration patterns gave signals indicating that structural integrity had begun to fail. The ice gave sound before it collapsed, but that sound was not heard by anyone at the time. Retrospective analysis noticed these warning signs. This time we are listening. The Ross Ice Shelf is being monitored continuously, automatically with high-precision systems, and this time, if the sounds change, we will notice. I hope we listen long enough before they change. I hope we can understand what the sound was saying before it falls silent. Chapter 21. SLEEP. Consciousness and ICE. Why does this sound induce sleep? Visual. Someone in deep sleep, a slow transition over ice shelf imagery. Sleep and ice are composed in visual parallel, both quiet, both endless. I have learned that this recording has been used by many listeners for sleep, and this both surprised and did not surprise me. It did not surprise me because sleep researchers have repeatedly shown that sounds with certain acoustic properties facilitate the transition to sleep. In particular, pink noise sound with a power that decreases linearly across the frequency spectrum improves sleep quality, and the vibrations of the ice shelf, in their processed form, approximately carry this pink noise property. Rhythmic sounds, sounds that repeat at regular intervals but change, also move us toward the delta and theta brainwave states associated with sleep. Just like the sound of rain or ocean waves inducing sleep, visual brainwave graphs, changing frequencies across sleep stages. Delta waves, deep sleep, are visualized. In parallel, ice vibration frequencies. What surprised me was this. This sound is also described as eerie. And normally eerie things are not expected to put people to sleep. But perhaps this is not a contradiction. Perhaps vast and incomprehensible things can give both fear and peace simultaneously, like sleeping beside the ocean. Hearing the sea is both calming and raises the question, what is out there? The sound of the ice shelf is like this. It draws you toward a center while simultaneously exceeding you. And when these two things happen at once, perhaps consciousness lets itself go, dissolves into something larger. This is the essence of sleep, releasing the self, and the Ross ice shelf is extending an invitation to that release, with its vibrations, its rhythm, its sound that you cannot understand but you can feel. Chapter 22, Phonography Preserving Sound. Transmitting sound visual, a historical montage from Edison's phonograph to today's digital recording technology. Summary imagery from the history of sound recording, black and white to color, analog reel to digital file. The invention of sound recording was one of humanity's greatest ontological revolutions. Before it, sounds were transient. A word was spoken and it was gone. A melody was played and it faded, a person's voice. After that person died, lived on only in the memories of others. After Edison's phonograph, it became possible to capture sounds on a physical medium. This was a revolutionary change. A dead person could now speak in their own voice. An orchestra from a century earlier could play again. Now we are taking this further. Not just human voices, we are recording the sounds of the world, the vibrations of glaciers, the murmur of the ocean floor, the pulsations of the sun, visual, digital storage, imagery, server centers, databases, digital archives, then a reversal, ancient air bubbles trapped in ice. Both are archives, both are time capsules. Ice is itself an archive. Air bubbles millions of years old, dust particles carried by ancient winds, volcanic ash all stored within the ice. This archive offers unique information about the history of the planet. And now, we are recording the ice's own vibrations, the voice of the ice itself, and transmitting this recording to future generations, perhaps in 100 years. The Ross ice shelf will no longer exist at this scale, and perhaps the people of that future will listen to this recording and think, that is how ice sounded back then. That is how large the ice was. And will this recording be a source of longing? A warning? A document of wonder? I don't know, but we are keeping the record. For now, that is enough. And keeping records is perhaps one of humanity's most beautiful qualities. We are transient, but the sounds we leave behind may outlast us. Chapter 23 contrasts ice and fire, cold and sound visual, a montage of contrasts, glacier and volcano, frozen silence and explosion, flatness and chaos, ice color, blue-white, fire color, amber red, dramatic but contemplative arrangement. Ice is the symbol of silence. At least, that is what cultural imagination tells us. But in reality, ice is extraordinarily loud, and this contradiction is worth thinking about. Fire represents sound and cultural symbols. Crackling, explosion, hiss. The acoustic world of fire is rich. Ice, on the other hand, is associated with cold and silence, but ice cracks, ice breaks, ice flows. Ice vibrates, and ice takes frequencies, amplifies them within itself, and transmits them again. If there were a competition for nature's sound amplifiers, ice would place very high. Visual, inside an ice cave. Ice stalactites, special sound recording equipment placed among them, an animation of sound waves propagating through ice. Ice caves, particularly semi-enclosed glacial caves, have extraordinary acoustic properties. In these caves, even the sound triggered by tossing a single small stone can create a resonance that lasts for minutes and grows progressively more complex. Ice is both partly sound reflective and partly sound, and this produces an environment that is simultaneously both loud and silent. This contradiction, both reflective and absorptive, both loud and silent, both apparently lifeless and yet felt to be alive, is the greatest magic of ice. And science explains this magic, but explaining it does not make the magic disappear. On the contrary, it deepens. Understanding the mechanism of something does not make it less wondrous, it makes it wondrous on a different level. When I learned the physical mechanism of the ice shelf's seismic vibration, that sound did not become less mysterious for me, only the address of the mystery changed. Chapter 24. Final listening, full data. Full sound visual. The screen darkens. Only the visual representation of the sound, a waveform animation, is visible. The waveform pulses, rhythmic patterns form. Color palette, ice blue waveform against a dark background. Now I am going to leave you alone. For a while, let the ice speak. Let me be silent. What you are hearing is the sound of a real geological process, carried to the human ear by scientific methods. The vibrations of the Ross Ice Shelf, the interaction between wind and ice, ocean loading, distant tectonics, thermodynamics. But what you are hearing is also more than this, the instantaneous record of a process, hundreds of thousands of years in the making. The acoustic expression of the sun's and the moon's influence on ice, the sounds produced by a planetary scale structure, the ice of a continent, while sustaining its own existence. Visual long duration, perhaps 10, perhaps 15 minutes of imagery and sound. Seismic data visualizations, footage from beneath the ice, the surface of Antarctica. Minimal editing. The ice speaks note. The length of this sound section should be calibrated to the video's total duration. This section forms the listening meditation core of the video. The viewer listens to the sound, imagery accompanies it. The narrator's voice withdraws completely. Chapter 25. Closing the ice is still there. Visual final imagery of the Ross Ice Shelf from above. Flight perspective, boundlessness, a sense of infinity. The camera slowly retreats, the ice shelf grows smaller, but it never disappears. The Ross Ice Shelf is still there in the moment you are watching this video. The ice shelf is vibrating. Wind is crossing the surface. The ocean is pushing from below. The sun is warming from above. And these three forces are continuously generating a melody the human ear cannot hear but technology can transmit. Science is recording this melody, analyzing it, trying to understand it, and in this effort, both practical knowledge and an unexpected beauty are being found. This video was made to share that beauty, the ghostly rhythm of the ice, the conversion of seismic hum to melody, the music of one of the world's largest structures, the ice of a continent, playing in its own natural frequency, continuously, without fatigue. Science could not silence it. Because science exists precisely to witness moments like this, to discover the music inside nature, in the next video we will listen to the sound of something else that is silent. But this week, the ice is enough. Visual, final frame. A distant shot of the ice shelf. The horizon, sky, no movement visible, or in fact everything is moving, but too slowly to see. The same ice, thank you for listening. Visual, the screen fades to black. In the final few seconds, from very far away, barely audible ice vibrations, then silence.